Hey guys, and welcome back to another video. Today we're going to be going over my very own original way of solving quadratics. This way of solving quadratics also doubles as a derivation of the quadratic formula. So if you're looking for alternatives to completing the square, then this video is for you. First of all, let's look at the four main ways of solving quadratics. First, we have factoring, which is pretty much my go-to method if we're dealing with quadratics with integer solutions. However, if the quadratic doesn't have integer solutions, then there's pretty much nothing that factoring can do for us, which leads us to the second method, completing the square. And completing the square is the main way that schools are going to teach the derivation and proving the quadratic formula. However, there actually happens to be other ways of proving the quadratic formula, which is what we're going to show in this video. So the third method is the Poche-and-Low method, which is this new way of solving quadratics created by none other than Poche-and-Low. And it happens to be another method to prove the quadratic formula. And finally, there's the Matophilia method, which is the method that I'm going to show you right now today, which I think I created on my own. If it exists already, well then that kind of ruins the point of this whole video. So hopefully it doesn't exist already, but that ends up being another way of deriving the quadratic formula, and it's just a way of solving quadratics on its own. So let's get into it. For the sake of this video, we'll be using a quadratic as an example, but you can do this for any other quadratic if you want to. So let's start with the quadratic x squared minus 10x plus 21 equals 0. So there are two things we know from this. First of all, we know, let's say that the roots are r and s. First of all, we know that r plus s is equal to 10 because the linear coefficient is negative 10 and the sum of the roots is negative 1 times the linear coefficient, which is 10. And we also know that r times s is equal to 21. And this is because the constant term is 21, and we know that the product of the roots is equal to the constant term. And if you don't know this as for a fact already, then, well, we can prove it pretty quickly. Let's say that we have a quadratic with the roots r and s, so we can write this quadratic as x minus r times x minus s equals 0. And when we multiply this out, we get x squared minus r plus s times x plus rs equals 0. And note that this is a positive rs because we have negative r times negative s and the negatives cancel each other out. So the majority of this proof is pretty much just manipulating these red and blue equations until we get something that isolates r and s so we can find r and s on their own. So let's start by squaring this red equation to get r squared plus 2rs plus s squared equals 100. And now let's multiply this blue equation by 4 to get 4rs is equal to 84. So now what we want to do is subtract the blue equation from the red equation. So we can say 4rs equals 84, and we can subtract these two equations. And note that you're allowed to subtract these two equations because you're subtracting the same thing from both sides of the red equation because 4rs equals 84. So you're subtracting the same thing from both sides, which is why it's allowed. So when you subtract these two equations, you get r squared minus 2rs because 2 minus 4 is negative 2, and then plus s squared equals 16. And the left-hand side of this equation just happens to be r minus s squared equals 16. So we have that r minus s equals to plus or minus 4. And so now we get two equations. We have r plus s equals 10, and we get that r minus s equals plus or minus 4. And now that we have these two equations, we have a system of two linear equations, and we can use these to find r and s on their own. And the fastest way to do this is to add up these two equations. So we have r plus s equals 10, r minus s equals plus or minus 4. And when we add these together, Well, the two s's cancel out, and that leaves us with 2r equals 10 plus or minus 4, and r is equal to 5 plus or minus 2, and that's our answer. These are the roots. But you might be wondering, well, what happened to s? Isn't there a second root s? So if r is equal to 5 plus 2, then, well, we can plug this in to the r plus s equals 10. So r is equal to 7, and that makes s equal to 3. So s is equal to 5 minus 2. And if r is equal to 5 minus 2, then s is equal to 5 plus 2. And so what this means is that one of the roots is going to be 5 plus 2, one of the roots is going to be 5 minus 2, no matter what. And that means that we're able to actually solve for the roots of this equation. That's it, we did it. So if you're wondering how this is a derivation of the quadratic formula, if you tried doing this method on a quadratic ax squared plus bx plus c, and you did all of these steps on that, then you would actually end up with the quadratic formula. And that's the whole mathophilia method. If you like this video, consider leaving a like or subscribing. Anyways, thanks for watching.